and welcome back. If you've already completed the first 3 lessons of this 5-part video series about the Session Initiation Protocol and you're ready for part 4, then you're in the right place. I think we've done really well covering crucial foundation concepts so far. We know about almost all the requests defined by SIP, their names and their purpose. We know about all the core headers within the SIP messages, what they're for and how they're used. We know about basic signaling for call management, how to establish a call, change the nature of a call, cancel or terminate a call. We know about network issues such as reliable delivery and potential delay, and how it's important to have an awareness of out-of-sequence requests. And we know about some anomalies and when some of our important rules get broken. In fact, I think we're ready to move straight on now to the next phase of our study, that of SIP servers and SIP services. There's so much to talk about with this topic that the lesson is divided into 2 parts. One of the first things we'll cover in part 1 of this lesson is the process of SIP location. So far we've been setting up calls dialing direct to contact addresses or to IP addresses, which of course is not ideal for the outside real world. Now, as part of this discussion, we'll look at other types of SIP addresses besides the contact address, and how through registering addresses with a registrar server, the location service can help us set up calls without having to already know the other guy's contact address. As we get into the world of servers and proxies, there'll be more we should cover on the routing of responses. We'll look again at the via header, and we'll see how SIP messages often include not just one, but a list of via headers. Then in the second part of this lesson, we'll take a deeper look at the routing of subsequent requests. Do you remember the route sets? We'll open the next chapter on route sets and look at how they affect the routing of requests, potentially through servers on the journey between user agents. We'll be looking at how, through mobility and forking, standard SIP services enable us to take our calls from different devices. There's no one-to-one binding between a telephone number or a personal identifier and a telephone or an endpoint. We'll spend some time on the redirection service, a service which gives us greater flexibility on how and where we receive our calls. Then we'll cover our last 2 families of responses, the 500s and the 600s, before finishing the lesson with a look at how the new world of SIP and the old world of the PSTN can actually live together, side by side, and peace and harmony. We'll take a look at gateways. One of the reasons why I love SIP so much is that, to my mind, it never said, here is a complete solution. Rather, it said, here are a set of tools, a set of facilities that you can use for your advantage. Tools and facilities like requests and responses, like the exchange and manipulation of media options, like SIP entities such as user agents. Now, included in that set of tools and facilities is another SIP entity worthy of discussion, the SIP server. The SIP server typically sits within the network and performs tasks on behalf of SIP endpoints. User agents, for example, often send SIP messages to the server with a view that it can perform some task on their behalf, some task that they perhaps might find difficult to do themselves. The SIP RFC, the specification, defines a set of services, basically tasks and behaviors that are implemented on SIP servers, all of which we'll touch on in this lesson. But as I said a moment ago, SIP doesn't claim to have a predefined solution to every requirement. In fact, quite the opposite. SIP says, look, if you want to, take these tools and these facilities that SIP defines for you and extend them to do even more interesting things, perhaps even things that we haven't yet thought of. SIP was designed to be extensible. Now, there's a whole bunch of SIP server type services that have grown and evolved over time that are not defined in the core SIP RFC. Now, SIP allows you to do these kinds of things because SIP was designed to be extensible. We'll come back and look at these kinds of services later in the last lesson. Let's take a look now at 2 standard SIP services, the Registrar Service and the Location Service. To put things into context, cast your minds back to one of the very first things we talked about in our first lesson. We said that SIP helps to establish a communication session. Now, SIP said right from the start, I will help you do 2 things. I will help the caller and the callee do something, and the caller and the callee know something else. Now, do you remember those 2 core tasks that SIP says it will do for you? What were they? SIP says, I'll help the caller and the callee exchange codec information so that both parties know which codecs to use for their media exchange. SIP also says I'll help the caller and the callee know where to send these packets, both the media packets and the signaling packets. Now when we think about all the SIP calls we've set up in these first 3 lessons, well, has SIP actually fulfilled these 2 tasks? In our calls so far, has SIP helped us to exchange codec information? And in our calls so far, has SIP enabled us to find the IP address of the other guy so that we can send him our packets? It was the first. Remember how in the payload of the invite, the caller sends to the callee his media options, including the codecs that he's willing to use for that call. Likewise, in return, the callee in the payload of the 200 OK sends back his media options, including his codecs that he's willing to use. So both parties now, through the exchange of these SIP messages, know what codec to use. So SIP has helped us here with exchanging codec information. What it hasn't helped us with is the exchange of IP addresses. Remember, if I want to make a call, let me clean up here. If I want to make a call between these 2 guys, I've got to shout over and say, hey, what's your IP address? 192.168.2.210, and you're listening on port 300 what? 3002. So now that I've obtained his IP address through my own means, I can go ahead and click dial, and on accepting the other side, the call is established. So SIP did not help me so far with initially finding the IP address of the other guy. So let's look now at how SIP does help us to find the IP address of the other guy so that we can make a call to him without first having to shout across the room or call him on our cell phones or something to find out what his IP address is. Let's talk for a moment about SIP addresses. We've seen already how the IP address of a user is included in his contact address. Now this contact address is sometimes known as a private address or a physical address. Now SIP also has the notion of a public SIP address made of a username and a host name prefixed by the letters SIP. It's this public SIP address that we'll give out to our friends. In other words, this is the address that they'll use typically to call us. Now the issue is, of course, if we were to send out a packet addressed to an address like this, dshepherd@avaya.com, it wouldn't know where to go. There's no inherent routing information within this address. So something somewhere has to be able to take this address and resolve it to a physical address or a contact address. So our next task then is to provide the information for that somebody somewhere so that when asked, they can make that resolution. Let's talk about the Registrar Service. I don't know what it was like back for you in your school days, but I have a clear memory of the schoolmaster taking the register at the start of each session. I guess you could say that he was acting as the registrar to record data in the registry, or the repository for registration data. Now, SIP Registrar is one of those core services defined by the RFC that we talked about earlier. It's just a server that has the capability to take registration data and to record it in the SIP registry, which more often than not is a database. So if we want others to be able to call us without first having to know our IP address, all we have to do is register with the registrar. Our registration includes both our public address and our private or contact address bundled together in a SIP register request that's sent out over the network to the registrar. When the registrar gets it, he unpacks the addresses from the request and writes them to the registry. From that point on, it's as if the server says, great, should anybody ask me from now on, I know that dshepherd@avaya.com is currently contactable at SIP 192.168.1.156 or whatever the contact address is. Now the idea is that everyone will register these details with some registry somewhere, so that should anybody ask for their whereabouts, their actual location can be resolved. So how about if we look at registration for real? Now I'm afraid that for this version of this lesson we don't have a registrar server for you folks to experiment with. It's certainly something I'd like to set up, but besides working out the physical mechanics of access and authorization, we'd also have to spend quite a bit more time here talking about authentication, firewalls, network address translation and those kinds of issues. We'd probably best talk about stun servers as well, all of which I think are more advanced SIP topics that I'd prefer to save for the SIP Advanced course. So for now, if you don't mind, I'll show you some things working and will ask you to do practical work in the context of analysing logs and scenarios that I'll be giving you. So I've got everything we need running on machines here on my desk. I've got user agents and I've got a server with registrar capabilities. For now there's not much to see about the server in any visual way, except I'll be running a tail so that we can see the logs of what SIP messages come into the server and what SIP messages go out from the server. I've also got an SQL database which we'll look at from time to time using MySQL query browser. So let's begin by taking a look at the database. Here's MySQL browser. I'll navigate to the database that holds a table for the registered locations. Now if I double click on it, MySQL query browser is kind enough to give me the SQL to go and query the database, and it comes back and I see that there are no entries in the database, no public URIs, no contact URIs. So with the database empty, I'll put the browser away for a moment and bring up the tail. There's no SIP messages having been received at the moment. I'll now switch over to another machine where I've got a user agent running. I'll just check its configuration. When we're doing anything but a peer-to-peer call setup with our user agents, we often configure what's called an outbound proxy, meaning that we're telling our user agent the address of a proxy which will be acting on its behalf. I've got my registrar server running on another machine on my desktop, so I'll type in its IP address, 192.168.2.210. That's the address of the outbound proxy. All the other details there look fine to me, so I'll click on Apply. I'll now go up to the Registrations tab. Now there's essentially 4 pieces of information that I need to give to my user agent so that it can construct a register request on my behalf. First of all, I need to give it the domain name of my SIP registrar. So I'll put in here sip:avaya.com. As well as having the domain name, I also need to tell my user agent where the registrar server actually resides. So rather than giving it an IP address, which I've already done here in my outbound proxy, I'm going to just click on this checkbox that says use outbound proxy. So now my user agent knows the domain name of the registrar and the IP address to which the registration request will be sent. The other 2 things are the addresses which I want to give to the registrar server, my public address and my contact address. Well, you can see that my contact address has already been picked up for me by the user agent. I better type in my public address, sip:dave@avaya.com. So I'm going to click on Add. As soon as I click Start, with a bit of luck, my user agent will construct and send that SIP register request for me. And straight away I can see from my tail here over on my other screen that the SIP request has arrived at the server and that the server responded directly with, guess what? A 200 OK, signifying or reporting successful registration. Looking at the database, if I run that SQL query again, we see that straight away there is now an entry on the database resolving Dave's public address to his contact address. The Registrar Service has written this information here to the database, to the registry. So how about you do a bit of practical now? Click here and download the server log so that you can see for yourself the actual SIP messages exchanged in this interaction just now. When you have them, check through the messages and the headers just to familiarise yourself with the registration process and to revisit the purpose of each header you find there. In fact, you'll probably soon notice that there are 2 new headers. Look out for them and identify them. You'll hopefully have noticed there's a new root header. Now we'll talk about the root header later in this lesson, so for now just tuck it away in the back of your memory and try and remember where you first saw it and in what context. The other header is the Expires header. SIP registrations often come with an initial period through which the registration will be valid, typically 3,600 seconds, the result of which is the registrar remembers that this registration is to be kept in the registry for just 1 hour, after which it will be removed. In fact, you can see the expiry recorded in the database. If I bring up MySQL browser again and scroll over, you can see here that along with the addresses recorded is the time of expiration. Can you go ahead and click here now to view another registrar server call log? Now I've just set things up so that it contains 5 register requests along with their responses. As you study the log, try and look for patterns as you go. I'm hoping that during the study you'll notice 3 main things. Now make a note of them and we'll discuss them together afterwards. I hope you noticed that 4 of the 5 register requests were from the same guy. from me in fact. Now looking at the requests, with the exception of the CSEC value incrementing, and we know all about why the CSEC increments, nothing seems to change. The headers in this first request here are just the same as the headers in the second request and in the third. It's not until we look then at the timestamps that things become apparent. This first request was received at 1654. The next request was received at 1724, exactly 30 minutes later. And if we go down to the next request, again 30 minutes later, 1754. These first three requests are exactly 30 minutes apart. What we're seeing here is re-registration. Although the user agent suggested in his first registration that he'd like it to last for 1 hour, 30 minutes later he decides to re-register, effectively buying some more time for his registration. So the registrar updates the registry with a new expiry time, meaning that the registration will stay there for another hour. Now the whole idea of this mechanism is that the registry, as much as possible, is kept up to date. Imagine the scenario where I were to register from my mobile device with no expiry and then my battery runs out so I can't use my phone anymore. It might be that for the rest of the day then the server thinks I'm available to take my calls, where in fact I can't. With expiring registrations though, within a reasonably short time, the server knows that I have not re-registered and therefore takes away my existing registration. In other words, he knows I'm not available to take any calls and won't bother to try and help set them up. Expiry times and re-registrations help keep the registry up to date. I'm going to scroll down now in my log to the fourth SIP message. Where is it? Okay, here it is. It doesn't take long when you're scanning through this message to see that we've got different addresses in the to and the from field here. So what do we have here? Well, of course, it's another registration from another user. It's a registration from Laurie, registering SIP Laurie at avaya.com, her public SIP address, to her contact address, SIP 192.168.2.4. She's registering for the standard 3,600 seconds, just like the other user agents. So this is another registration. Another registration, a new registration. Now we have two users registered with the registry. And if I open up my database query browser again and take a look at the database and run that script, we see that we do in fact have those two addresses, two public addresses and two contact addresses, two registrations on the registry. So following the register we have from Laurie, I'll scroll down a little bit and we find we've got another registration from Dave. Looking at the timestamp, it's not actually 30 minutes later. It's a little bit sooner than 30 minutes. When I scan down through the message, I see that CSEC value has incremented, but look at this. The expires value is 0. This is SIP's way of unregistering. If a user agent wants to go offline, he just sends another register request, but populates the expires header with 0. This is the key for the registrar to remove the entry from the registry. I see the register request a little like a letter that we could perhaps send to the server saying something like, Dear avaya.com server, please arrange for all incoming calls to SIP Dave at avaya.com to be forwarded to SIP 192.168.2.3. Thanks very much. Lots of love from SIP Dave at avaya.com. Oh, and by the way, please send your confirmation of this request back to me on the address above. So how about this then? What if I, that's me, SIP Dave at avaya.com, sent a similar letter to the registrar, but I changed the address in the to header and the contact header? What if I give a different set of public and contact addresses to the registrar? Now pure SIP says the registrar would process them just the same. In fact, SIP provides a mechanism for third-party registrations for someone like me to perform a registration on behalf of someone like Nathan. Now, although there's issues with security and authentication, which we'll not get into here, this is a great way for a service provider or someone to register endpoints that perhaps can't register for themselves. A plain old telephone, for example, one that doesn't understand SIP. We'll be talking later in this lesson about interacting with non-SIP telephones. So, third-party registrations. Let me give you a quick demo. So here's my user agent. We can see the from address is from me, SIP Dave here. Let me go to the registrations tab. I've already registered myself. We can see the to is sipdave@avaya.com, from myself, sipdave@avaya.com, with my contact address, 192.168.2.210. But now I'm going to perform that third-party registration on behalf of my colleague Nathan. And I'll put in his contact address. I'm going to make one up now. Let's say it's on 165. And we'll give him the standard port of 5060. And I'll add that and start it. And straight away my third-party register request gets sent off. And the registrar sends me back a 200 OK indicating the registration has been successful. I'll just check on the database and run that query again. And I see that Nathan's public address and his contact address have been stored on the database. So finally we have the last of our 6 standard SIP messages. The register request, used of course to register our public address and our contact address with the registrar, with the intention that the server will then help others to set up calls with me using not my IP address but my public address. In fact, that's the next topic we'll look at together, how a server helps set up such calls. We'll be looking at the location service. But first, why not review some of the points we've discussed so far? Let's take a look now at the location service. Imagine the scenario in which me, Dave@avaya.com, wants to make a call to my friend Sue at elsewhere.com. The only trouble is, I don't know where she's contactable. I don't know her IP address. I need some help, and I'm going to try and get it from my Outbound Proxy, a proxy who knows how to act as that location service on my behalf. So that's where I'll send my invite to my default Outbound Proxy, acting as a location service. I'm guessing you're anticipating now what happens next. Well, actually, maybe there's a little more than just looking up the registry. Let's take a look at what happens under the hood. Now I've rearranged things here a little, but here's my request arriving at the server. From a location perspective, the first thing the server does is check the domain name in the URI of the incoming request and ask the question, am I the controller of this domain? And of course it goes off and checks its configuration to find out. I've configured my server here to have responsibility for avaya.com. If the answer is yes, there is a match between the domain name in the incoming invite and the domains that I control, then I will do the database lookup that you've been anticipating and will proxy or forward the request on direct to the invited party, to the resolved contact address. Easy. What if the answer is no? What if the server is not the controller of the domain? Well, think for a moment about Sue and the things she will have done in order for us to call her using her public address rather than her contact address. Sue will have needed to have registered. Now, where will her registration details be stored? On the avaya.com registry? No, not there. So if not there, where will her registrations be? Sue's registration details will be on the elsewhere.com registry. So if Sue has registered with her registrar, the elsewhere.com registrar, then of course there's no point in the avaya.com location service looking at the avaya.com registry. Looking in the avaya.com registry, there'll be no reference there to Sue. So what do you suggest the avaya.com server should do now? Indeed, it should forward the request downstream to the server that does have control of the elsewhere.com domain, in other words, the elsewhere.com server. But how now does it know where the elsewhere.com server is? How can it find the elsewhere.com's IP address for forwarding the invite to the right place? It does a DNS lookup. That's one of the things I love so much about SIP. SIP does not try and do everything itself. If there's a perfectly good domain naming service out there, why not use it to look up and resolve domain names? That's exactly what SIP does. SIP uses DNS. So if the DNS lookup returns an address, then of course the invite is proxied downstream to that address. But what happens, do you suggest, if DNS fails to resolve the domain name to an address? If DNS fails to resolve the domain name to an address, the server simply returns a 404 not found error message back to the caller, and the call does not get set up. I remember reading for the first time about the SIP location process and getting the distinct impression that the location service will do almost whatever it takes to find you wherever you are, almost magically, and set up your calls. In the real world, there's nothing magical about the location service. It will only find you if A, you have registered with a registrar, and B, your registrar itself has registered with DNS. If either of these two registrations are missing, the location task, and therefore the call setup, will fail. So going back to our scenario, when the server receives my invite to Sue, what's the very first thing it will do? I bet some of you suggest the server would perform that location task, either checking to see if the request is addressed to someone in one of its controlled domains or doing a DNS lookup. Now it will do those things, but not yet. Think back to basics. First it will construct and send a 100 trying, confirming reliable delivery of that request back to the user agent client. Only then does it check to see if it's the controller of the invited party's domain, and on realizing he isn't, does a DNS lookup and finds that the elsewhere.com server resides just up there in the top corner of the network. He then of course forwards the invite to the elsewhere.com server. Again, when the elsewhere.com server receives the invite, what's the first thing that it now does? Just like the avaya.com server upstream, the very first thing the elsewhere.com server does is to create and send the 100 trying to confirm reliable delivery across this hop. Remember, the avaya.com server is responsible for reliable delivery across this hop between these two servers. Oh, notice how the 100 trying is not sent further back upstream to the user agent client. Remember how reliable delivery is only over a hop-by-hop basis. Now, only after sending the 100 trying does the elsewhere.com server attempt the location task, or in other words, to ask that same question, am I the controller of the domain in the request URI of this invite, or should I do a DNS lookup? Of course, he realizes pretty quick that he is the controller of the elsewhere.com domain and jumps straight into a lookup on the local registry to see if Sue has registered, and if so, to resolve or find her contact address from her public address. The registry looks up and returns the fact that Sue is registered and that she is contactable in this location. So the server, having just acted as a location service, now acts as a proxy and forwards that invite downstream to Sue's contact address, following which of course Sue responds directly with her 100 trying. What happens next? Sue creates and sends a 180 ringing. Unlike the 100 trying, the 180 is for the upstream user agent endpoint, not so much for the servers. So the question is now, over which route should the 180 ringing be sent? To answer that question, first of all, let's think about what we already know about the routing of responses. Secondly, let's think about what makes logical sense. Should the response go back to the upstream user agent client directly, or should it go over the same path as the request in reverse order through the servers? Let me ask a different question. Does Sue actually have address and routing information sufficient to send the response direct to Dave? If so, where from? The answer is yes, Sue does have Dave's address from his contact header. So technically it could be possible to send the response directly to Dave. This is not how the routing of responses works though. We already know that responses are always routed according to the address in the what header? The address in the via header. We'll prove shortly that all responses, after the 100 trying that is, are not routed direct between SIP endpoints, but are routed back over the same path over which the request travelled downstream. The 180 ringing therefore travels from Sue to the elsewhere.com server, to the avaya.com server, and on to Dave. Although it might be interesting for the servers to see the 180, the important reason for routing responses over the same path as the request in reverse order is much more apparent in the context of the final response. Now, what reasons can you suggest why it's important for a server to process the final response on its way back upstream? Think about it now, and I'll give a clue just in case you need one after you press play, following which you can then make a note of your thoughts. Okay, so here's the clue. If I were to mention the words stateful and stateless servers, would that help at all? The reason why servers might need to process the final response is to help them, perhaps after the fulfillment of the location task, release any related resources they may have kept relating to this call. Servers typically, although not always, act in stateful mode, meaning that they remember things about an interaction, so that later, when they need to perform some subsequent task, they can bring something back from memory to help them in that processing. I like to think of the server, and particularly the action of processing requests, somewhat like it having a brain with some thinking space. When the request first arrives, the server kind of says, right, I'm going to allocate some of my resources, my memory, my thinking space to the processing of this request, and I'll need to remember a few things related to it. For example, I'll need to keep a copy of the request just in case my reliable delivery timer expires and I need to retransmit the request. The same thing happens at the downstream server after the request has been proxied. It too allocates some thinking space to store all the things it needs to remember to manage this interaction. Now, if these servers allocated some thinking space for each call they processed and never released those resources, then of course all of their memory would eventually be used up and the server would fail. SIP says a response must always follow the same path as the request, in reverse order, not just to give each server a chance to know that the call is set up successfully, but at very least to give them a chance to release associated resources. Thus, when the final response is received, the server may well clear out its state, making those resources available for use on other calls. And as the final response travels upstream, each server has an opportunity to do likewise. Remember the rule, SIP responses always follow the same path as the request, in reverse order. Ignoring the ACK for a moment, with the caller's media options being delivered in his first invite, and the callee's media options being delivered back in the 200 OK final response, both parties are ready now to start the conversation, ready to start exchanging media packets. The next question then, over what route do the media packets travel? The media packets are routed to whichever address is supplied in the media options from the invite and from the 200 OK. Typically, the addresses of the endpoint user agents, meaning that the media stream is established direct between the two SIP endpoints. Note how the media packets never travel through the servers. The role of standard SIP servers is to process signaling packets, not media packets. So let's take a look at the location service in operation. I've got a user agent over here, and we can see when we look at the registrations tab that he has registered his public address sipjohn@avaya.com and the registration has been received successfully. I've got a tail application in the middle here watching the calls log of my SIP proxy, ready to print out any SIP messages that it receives, and I've got my upstream client user agent ready to make the call through to John's public SIP address that I've already typed in. However, if I go to the configuration tab of this user agent, notice that I have not yet set the outbound proxy, meaning that this user agent is working on his own. Neither does it have any DNS service through which any domain names can be resolved. So I'll go to my Sessions tab, I'll click on Dial, and straight away the user agent comes back with the 404 not found. It doesn't know where avaya.com is, it doesn't know who John at avaya.com is. This time I'm going to go to my configuration tab and type in the address of the outbound proxy 192.168.2.210 and apply that. And this time when I go back and click Dial, straight away you can see that the request has been forwarded on downstream. The messages have just appeared there a few moments later in the tail application, and the downstream user agent is alerting. I'll go and accept that call now. The call is set up and the media stream is established just as we've been describing. I'll hang up the call now, and looking at the tail, we can see here we've got a good healthy set of SIP messages representing the call flow of the call setup. Okay, you're getting quite some experience of SIP call flow now. How about you make a prediction about what messages there are in this call setup? Take some paper and a pen and sketch the flow of SIP messages between the 3 SIP devices required to establish the call. Then label each message with a request or response type. Think about it. Remember the rules and the exceptions, and you should be able to do it just fine. Don't worry for now about terminating the call. We'll cover that later. There are some interesting things to observe from this call flow. In fact, can I ask you to click on the link here and download the call log my server made as it set up another call. Then we can take a look at it, not just at the flow of messages to check our predictions and our call flow map we drew just now, but at some other things which might help us become more familiar with SIP and with how SIP works. Remember that this is the server log. It shows messages as they arrive at the server and as they leave the server. So by comparing an incoming message with an outgoing message, we can see if the server has made any modifications. Your task now is to study the log and make some general observations before being presented with some more specific things to look at. You might find 1 or 2 surprises. So let's look at those questions together. Here's the log file that you should have, and I can quickly see by looking at the from header that the caller was sipbob@avaya.com, and by quickly looking at the to header, the call was made to sipjim@avaya.com. Nice and easy. Now, regarding the number of messages in the server log, I wonder if any of you are surprised to see that there were only 1, 2, 3, 4, 5, 6, 7, 8. 8 messages. Something seems to be missing. Not the old black sheep again, is it? Well, more on that later. Let's look now at the 4 changes between the incoming invite and the outgoing invite. The first thing I hope you noticed was that the request URI has changed from a public address to a contact address. And we know why, don't we? The whole reason why we're using this server is to have it perform a location service for us. We give it a public SIP address, and the server queries the registry to get back the related contact address, which it then physically copies into the request URI of the SIP request before sending it downstream to that address. Now, another change I hope you noticed was the addition of another via header. What do we know about the purpose of the via header? The via header is for routing responses. In fact, we just discussed a moment ago about how responses must travel over the same path as the request, in reverse order, so that servers along the way have an opportunity to see what's happened, and more importantly, an opportunity to tidy up any state, to release resources. The question is, though, how does SIP handle the routing of responses over this same path? How does it know the path over which a request has travelled? The answer is through the via header, or now more specifically, the via headers, or the via list. Here's how it works. Imagine a scenario in which we have 3 servers between the 2 endpoints. Remembering the purpose of the via header is for routing responses back over the same path as the request, the upstream user agent sends out his invite and, wanting a response back from the server, adds his own address in the via header. On receiving the request, the server immediately copies the via header from the request into the newly created 100 trying response and sends that response back upstream, routing it to the address in the via header. The server then processes the request and, in this scenario at least, sends the request on downstream. But just like the user agent before, it too wants a response, so it adds its own address to the top of what is now a list of via headers. When server 2 gets the request, it knows to send the response to the top address in the via list, back to server 1. Now don't forget, of course, that 100 responses are for reliable delivery only and don't therefore get propagated upstream. Now server 2 and server 3 do likewise, adding their addresses to the top of the via list as via headers. In other words, supplying routing information so that the guys downstream know where to send their responses back. By the time the request arrives at the destination, the via list now includes a record of the path over which requests have travelled downstream. In fact, I've heard some SIP commentators say that the purpose of the via header is to do just that, to record the path over which a request has travelled. Now, whilst this is true, my feeling is that they've kind of missed the point somewhat. To me, the reason for the via header is for routing responses back over the same path. If we consider the record of the path and don't consider why we need that record, then we too have missed the point. Remember, the via header is for routing responses. We know that the complete via list is copied into the response. We also know that responses, other than the 100 trying, are routed back over the same path as the request, all the way from user agent server, through the servers, back to the user agent client. Now I hope you can see how it works. See here how the final response is sent upstream to the top address in the via list, routing it back to server 3. Now when server 3 receives it, it kind of says, great, I've got my response. The address I added to the via list has served its purpose, but I see that there are other addresses in the via list, meaning the response is not just for me. I'll strip off my via header and will send the response on upstream to the new top item in the via list. The same thing happens at server 2 and server 1 and so on. They strip off their own addresses, and if there are still addresses remaining, they forward that response upstream to the topmost address in that via list. Note how, when the response arrives at the user agent client, the record of the path over which the request has travelled has dissolved. The purpose of the via list is not to record the path just because it seems a fun thing to do or because the user agent client might like to know where the request has been. But more importantly, remember, the via list is to record addresses for the routing of responses. I hope you note that we've also just answered the fourth question, the difference between the 200 OK as it arrives and leaves the server. We saw that the topmost via header there, the one belonging to the server, was stripped off before the response was sent upstream. The third thing I hope you noticed between the incoming request and the outgoing request at the server was that the max forwards header was decremented. The purpose of the max forward header is to stop a request from continuous looping. Now imagine a scenario in which a request is sent out from a user agent with the default value of 70 in its max forwards header. Server 1 does as it's supposed to do and decrements the max forwards header before sending it on downstream, as does server 2. Imagine though a problem occurring at server 3, one in which perhaps the lookup process incorrectly results in the request being sent back to server 2. Server 2 will probably process the request in just the same way it did before. If it found a reason to send the request to server 3 last time, then it will probably do so again now, as indeed might server 3 again. You can see what's happening here. Looping is taking place. Without the max forwards header, this looping might continue forever. But fortunately, the decrementing max forward header prevents the loop from continuing forever. As soon as a server realizes the max forwards value is 0, it promptly creates and sends back a 483 too many hops error response, politely informing folks upstream that the request has not made it through to the intended endpoint because of a looping problem. Incidentally, the response travels back over exactly the same path as the request, just like we discussed a moment ago. Imagine how big the via list can get when looping takes place. Huge! Up to 70 addresses in the via list in a single request or response. If you ever see a huge via list in a log file, you'll know immediately what's happened. You can't miss it. The max forwards header is to prevent illegal looping.